Hello, General Biology, and welcome to the third in the screencast series for Chapter 5 on our supplemental material outlines that you're looking at. And yet the last screencast, we were talking about density-independent factors, and a density-dependent factor, and a density-dependent factor was a factor that depended on the number of living things that were present, so we called it biotic. And we used the example of predator-prey relationships. That's the easiest and the most common. And we talked about the prey. If there's not enough prey, there's going to be smaller numbers of predators. And if there's too many predators, then that's going to limit the prey. So it was living things that determined whether the organisms were going to be abundant or not. Today we're going to talk about density-independent limiting factors, and this is anything abiotic. And what we have to keep in mind about this is they're going to affect all populations regardless of size. So it doesn't matter if we're a small number of organisms or a large number of organisms, it's going to happen either way. So these are non-living things, and weather's the most obvious. Hurricanes, droughts, floods, those types of things that are independent. So if we had an island that had 5 rabbits on it, that hurricane's going to hit that island, and since there's only 5 rabbits, probably it would kill out all the rabbits, versus an island that if we had 500 rabbits and it hit, there would be a greater chance for those rabbits to have some that could survive and repopulate over a few years. So we also consider natural disasters like wildfires and volcanoes and earthquakes, keeping in mind that human activity, the building on the land and the plowing under the prairies and the cutting down of rainforest has already stressed ecological communities. So they might not be able to recover as easily from a natural disturbance. So we call these density-independent limiting factors because it doesn't matter. They're independent of the number of organisms that live there. It's just going to happen. Okay, so let's talk about the human population and human population growth. This is section 5.3. So take a look at this graph, and we can see that from the beginning of man, the population numbers were really relatively small. It wasn't until about this point in time, maybe 5,000 years ago, when plowing and irrigation started to come in, that we saw population numbers begin to nudge just a little bit and increase some. When we get to about the year 1400, there was the bubonic plague, and that wiped out a large portion of the population. It was carried by fleas. So cleanliness, we found out was next to godliness. If you weren't clean, you were going to go see God pretty soon because you would get fleas. So that was a problem. And then as soon as the Industrial Revolution began, we're talking about 1800s, 1900s, we see the population begin to grow and continue to grow. We're about 7.4 billion people now across our planet. So take a look at this curve. What does it represent? Exponential or logistic? And I'm hoping you're all saying exponential, Mrs. Saunders, and you're right, that's exponential because it's a J-shaped curve and the resources appear to be unlimited. Well, scientists are predicting that by the year 2050 we might reach our carrying capacity, and this might take a logistic S-shaped curve where we start to level off and even decline. So when we look from this point to this point, it took about 123 years for the human population to double, to go from 1 billion, I should say from this point to this point, go from 1 billion to about 2 billion. And then in from 1804 to 1927, another 33 years for it to double again. So it wasn't too long after that where it started to double, and that's the way that we've been going. Let's take a look at this video.
You know, there are a lot of things that we can fix in this world. We can do something about. We can design the cities that we live in, the kinds of houses we live in, the market, the economy, currency, how many trees we're going to cut, how many fish we're going to catch. Those things human beings can manage and control because we create them and do them. But some things are facts of life. We have to live with the speed of light, gravity, entropy, the first and second laws of thermodynamics. Those are things that we have to accept and work ourselves around. And there is another one that is absolutely crucial. It's a mathematical reality called exponential growth. If something is growing at 1% a year, it'll double in 70 years. 2% a year, it'll double in 35 years. 3% a year in 24 years. 4%, 17.5 years. Anything growing exponentially will double in a predictable length of time. Now I'm going to show you why all of this stuff about we got to keep growing, keep the economy growing, we've got to keep everything growing is ultimately suicidal. I'm going to give you a system analogous to the planet, and that's a test tube full of food for bacteria. So the test tube and food is the planet, and the bacteria are us. Now I'm going to introduce one bacterial cell in, and it's going to divide every minute. That's exponential growth. So at time 0 at the beginning, there's one cell. 1 minute, there are 2. 2 minutes, there are 4. 3 minutes, there are 8. 4 minutes, 16. That's exponential growth. And at 60 minutes, the test tube is completely packed with bacteria and there's no food left. So we have a 60-minute growth cycle. When is the test tube only half full? Well, of course, the answer is at 59 minutes. Even though it's been chugging along for 59 minutes, it's only half full, but 1 minute later, it'll be completely filled. So that means at 58 minutes, it's 25% full. 57 minutes, it's 12.5% full. At 55 minutes of a 60-minute cycle, it's 3% full. At 55 minutes, one of the bacteria says, hey guys, I've been thinking, we got a problem. We got a population problem. The other bacteria would say, Jack, what the hell have you been smoking, man? 97% of the test tube's empty and we've been around for 55 minutes. And they'd be 5 minutes away from filling it. So, say bacteria are no smarter than humans. At 59 minutes they go, oh my God, Jack was right. We got 1 minute left. What are we going to do? Well, don't give any money to those economists that are saying we got to keep growing all the time. Give it to those scientists. So they massively inject money into the scientific community. And guess what? In less than a minute, those bacterial scientists invent 3 new test tubes full of food. That'd be like us finding 3 more planets that we could use. What happens? At 60 minutes, the first test tube's full. 61 minutes, the second's full. 62 minutes, all 4 are full. By quadrupling the amount of food and space, we buy 2 extra minutes. Our home is the biosphere. It's fixed and finite. It can't grow. And we've got to learn to live within that finite world. Every scientist I've talked to agrees with me. We've already passed the 59th minute.
So what are your thoughts? Do you think we've passed that 59th minute? There are some scientists that believe that we are there, but economists believe that scientists are going to be able to solve the problem. And they'll only be able to solve the problem if people listen to them, especially like our politicians would listen to them. So the next part of the chapter, we're going to talk about the patterns in human population growth. And the study of the human populations is referred to as demography. And the scientist that studies those patterns is known as a demographer. So they look at the characteristics of human populations and how they change over time. So they'll take into consideration the immigration, emigration, the death rates, the birth rates, and all of that might have an effect on the population numbers. They look for countries to undergo something called demographic transition. And you might also hear me refer to this as industrialization. And what that means is that the country is actually going to go through a change where they go from having low technologies to advanced technologies, and education and the economy improves. So we can take a look at these two age structure pyramids and we can see here's Guatemala, a place with a very, very high birth rate, but yet a very high death rate. People around the age of 34 to 35 are really considered their senior citizens, and then the numbers start to rapidly drop off. Where when we look at the population in the United States, here's our baby boomers. These are the children that were born in 1953 to about 1963 because of the war that was going on. And we see that we still have, fairly high amounts of births, but the people are living longer. They don't really start dying off until they're in their 60s, where it drops off. We're going to take a look at a video on this, but we're going to do this on the next screencast. So I'm going to stop this here, and I'll see you in a minute or two. Bye.